All right, in 6.4, we're going to be looking at the sampling distribution of sample proportions. All right. The sample proportion, p hat, is the statistic that we use to estimate the unknown population proportion, p. Notice it's without a hat. To understand how much p hat varies from the population proportion and what values of p hat are likely to happen by chance, we want an understanding of the sampling distribution of sample proportion. All right, sampling distribution, here's your definition of sample proportion, describes the distribution of values taken by the sample proportion in all possible samples of the same size from the same population. All right, so you're taking many, many samples and measuring some proportion of that sample, and you're making a dot plot of all the proportions that come out from all the different samples. That's what this is talking about, and we'll try to do some simulation in class. There are formulas that describe the center and the variability of the sampling distribution of p hat. All right, so we want to know what the center is and what the standard deviation is. So here's your box. You need to fill this information in. So suppose that p hat is a proportion of successes in a simple random sample of size n, drawn from a large population with proportion of successes p. Then the mean of the sampling distribution of p hat is, and that's how we notate it right here, the mean of the p hats is equal to p. Remember, this is the population proportion. Okay? That's the population proportion. So the mean of our samples will always equal the population proportion. So really there's no calculation here. You just have to understand this relationship. Now to get the standard deviation of the sampling distribution of p hat, there is a formula. So notice what it is. It's p times 1 minus p divided by n, which is our sample size. And p will be given to you. The population proportion is given. Okay? So you'll see that as we will do a problem. But write these formulas down. We'll come back to them in a minute. Both the sample size and the proportion of successes in the population affect the shape of the sampling distribution of the sample proportion p hat. The shape of the sampling distribution of p hat will be closer to normal when the value of p is closer to 0.5 and the sample size is larger. So, all this is saying is that in order to use normal CDF function in our calculator, we got to prove that this distribution is normal, okay? And we got to figure out, okay, how big does it have to be normal? All right, and there is a condition called the large count condition. That's what this is saying. It says, suppose p hat's a proportion of successes in a random sample of size n from a population with proportion of successes p. The large counts condition says that the distribution of p hat will be normal, approximately normal, when n, sample size, times p, the proportion of the population, when you multiply those two and you get greater than or equal to 10, and, notice it's not or, it's and, n times 1 minus p is greater than or equal to 10. When the large counts condition is met, we can use normal distribution to calculate probabilities involving p hat, which is the proportion of successes in a random sample of size n. So large counts condition is the big picture on this one, and we'll talk more about this in class. All right, so let's do some problems here. It says the makers of Skittles claim that 20% of Skittles are orange. You select a random sample of 20 Skittles from a large bag. Let p hat equal the proportion of orange candies in the sample. All right, so p hat is a proportion, and we would find that by taking however many orange, and we would divide it by the total number of 20 candies in your sample, and that would give us some decimal answer, some percentage answer. That's what p hat is. Now, just imagine if I give you 20 Reese's Pieces, would exactly 20% of them be orange? Well, probably not, but your sample would have some orange probably, so we'd figure out what percent that would be. So to calculate the mean standard deviation, okay, remember the mean, previous slide said the mean of our p hats is equal to the population proportion. So we got to look back at our question. What does it say the population proportion is of orange candies? Well, right here it says the makers of Skittles claim that 20%, so P is 0.20, are orange. So the mean of my sampling, all my samples would be 0.20. Easy enough. Now, standard deviation, to find the standard deviation of P hat, so use those symbols. We use that big old square root. Remember, the formula says P times 1 minus P over N. So let's rewrite this in terms of our problem. The p-value is 0.20. 1 minus 0.20 divided by our sample size of 20, so N was 20, and take the square root of all of that. All right, so put this in our calculator. Times 1 minus 0.20 is 0.80. Okay, divided by 20 equals that, and I want the square root of that. And there's my answer. So my standard deviation is 0.0894. 0.0894. All right. B, interpret the standard deviation from part A. So here's right here, we got to interpret this. Remember, standard deviation is always the typical distance from the mean. So what we would say is that the sample proportion of orange candies typically varies from the mean about 0.0894. Okay, so that's about 8%, 9%. Okay, the sample proportion of orange candies typically varies from the mean about 0.894. So you will have to interpret some standard deviations after you've calculated them. Number 2, the Transportation Safety Administration, TSA, is responsible for airport security. On some flights, TSA officers randomly select passengers for an extra security check before boarding. One such flight had 120 passengers, 16 in first class, 104 in coach. TSA officers selected a simple random sample of 10 passengers for screening. Would it be appropriate to use a normal distribution to model the sampling distribution of P hat, or the proportion of first class passengers in the sample? Okay, so let's think. Okay, the proportion of first class is going to be first class over the total. All right, so to find P, we think, okay, what's the number of first class over the total number of passengers? It says there's 16 in first class over 120 total passengers, right? So, and our sample size is 10. So we have to use that large counts test. Remember, the large count test says N times P has to be greater than or equal to 10, and N times 1 minus P has to be greater than or equal to 10. All right, so we know that P is this fraction right here. 10 is our N, so I say 10 times 16 over 120. And if I put that in my calculator, I get 1.3. Not greater than 10, right? So let's look over here. 10 times 1 minus 16 over 120. That comes out to be, let's see, 8.67. Well, okay, we have a problem because this is not greater than or equal to 10. Doesn't work. This is not greater than or equal to 10. Doesn't work. So it's saying, can we use a normal distribution? No, we cannot. So we would say, no. We would say the sample is not large enough to use a normal distribution. It does not pass the large counts condition, right? So you run the large counts condition, and if they come out greater or equal to 10, then you're good to go. But if they don't, then no, you can't. It's not large enough to use a normal distribution. It does not pass the large counts condition. That's what you have to explain. Number 3. Suppose that 70% of all college women have been on a diet within the last 12 months. A sample survey interviews a simple random sample of 267 college women. Find the probability that 75% or more of the women in the sample have been on a diet. All right, so we have a lot to decode here and figure out. Our goal is to do a normal CDF calculation, but in order to do that, think about normal CDF stuff. You have to know the mean and you have to know the standard deviation. All right, so the mean of our proportion, remember, is that's equal to the population. Well, what is the population proportion? Well, we're talking college women, and here's the population proportion right here, 70%. And we know that's equal to the mean of our sample. So our mean is going to be 0.7. Our standard deviation, we got to calculate that. We would do 0.7 times 1 minus 0.7 divided by 267. Hopefully you'll begin to see this pattern. You'll see 0.7 times 0.3 over 267. And if I calculate that, I get 0.028. All right, so there's standard deviation. So now you would draw a picture, okay? Visualize what's going on. We need to check, does this pass, can we use this? So we have to figure out, does it pass the large counts test? So we do n. So we do n, which was 267. 267 times 0.7. And we got to do 267 times 1 minus 0.7. And see, are these greater than or equal to 10? If they are, we can use our normal distribution. Let's check that out. So we have 267 times 0.7. Oh yeah, 186 is definitely larger than 10. Check, that works. Then we do the other one. 267 times 0.3. So 80 greater than or equal to 10. So we are in good shape. So we can use our normal curve. So now we can draw this in. We know our mean right here is 0.70. So now we look at the rest of the question. It says find the probability that 75% or more of the women in the sample have been on a diet. So if this is 0.7, 0.75 is over here. And it says or more, so I'm going to shade this way, right? So now we're back to our normal CDF function. Our lower bound is 0.75. Upper bound is positive infinity. Our mean is 0.70. And our standard deviation is what we calculated, 0.028. And then we would find our answer from our calculator. 0.0371. And there's my probability. And that's what we've got to do. So it takes a little bit of work. You've got to find the mean and standard deviation. You have to test for large counts. If it passes, then you can do this and run the normal CDF. Okay? So hopefully this gives you a good standard to follow, and we'll talk more about this in class.